A monumental leap in our quest to understand the universe's most elusive particles has just been achieved deep beneath the Earth. On August 26th, a new era in particle physics officially began as the colossal Jiangmen Underground Neutrino Observatory, JUNO, was powered up, marking the successful activation of the world's largest and most sophisticated neutrino detector. This momentous event, the culmination of over a decade of meticulous planning and construction, positions JUNO at the forefront of a new generation of massive-scale experiments designed to unravel the deepest secrets of the cosmos. And here's the truly exciting part. Initial data from its trial runs indicates its performance isn't just meeting expectations, it's surpassing them, setting the stage to answer one of the most profound and stubborn questions in modern physics. But here's where it gets controversial. The answer JUNO finds could completely upend our current understanding of the fundamental laws that govern all matter. The core mission of this behemoth is to definitively solve the neutrino mass ordering puzzle. In simpler terms, scientists want to know the precise hierarchy of the three different mass states that neutrinos can have. Think of it like trying to figure out if three mystery boxes are stacked from lightest on top to heaviest on the bottom, or in some other order. JUNO's specific goal is to determine if the third mass state, known as nu3, is actually heavier than the second, nu2, a finding that would be a cornerstone for all future physics. Professor Yifeng Wang, a lead researcher at the Chinese Academy of Sciences Institute of High-Energy Physics and the spokesperson for JUNO, captured the significance perfectly. Getting the JUNO detector filled and beginning to collect data is a historic milestone. For the very first time, we have an instrument of this immense scale and precision that is entirely dedicated to studying neutrinos. What this means is that JUNO will finally allow us to answer some of the most fundamental questions we have about the nature of matter and the universe itself. So, how does this incredible machine actually work? Nestled 700 meters underground near Jiangmen City in Guangdong Province, China, JUNO is strategically positioned to detect antineutrinos, the antimatter partners of neutrinos, that are generated an exact 53 kilometers away by the powerful Taishan and Yangjiang nuclear power plants. Here's a key point most people miss. Unlike other methods for determining mass ordering, JUNO's approach is uniquely independent of the distorting matter effects caused by the Earth's interior. This makes its eventual result incredibly robust and largely free from confusing statistical overlaps or parameter degeneracies. Its record-breaking precision won't stop there. JUNO is also poised to deliver measurements of other neutrino oscillation parameters that are 10 times more accurate than ever before. Furthermore, it will serve as a premier observatory for studying neutrinos from a vast array of sources, including our Sun, distant supernova explosions, Earth's own atmosphere, and even the planet's interior geology. It will also open brand new windows into exploring unknown physics, such as the hunt for hypothetical sterile neutrinos, a proposed fourth type, and the extremely rare process of proton decay. The journey to this point was a marathon of human ingenuity and international collaboration. First proposed in 2008 and officially approved in 2013, the project began its underground construction in 2015. The incredibly delicate installation of the detector components started in late 2021 and was finally finished in December 2024, leading to a carefully phased filling operation. In a breathtaking feat of engineering, the team filled the cavern with 60,000 tons of ultra-pure water in just 45 days, all while maintaining a liquid-level difference between the inner and outer spheres of mere centimeters, and keeping the flow rate uncertainty under an astonishing 0.5% to protect the structure's integrity. Over the subsequent 6 months, they then carefully filled the massive 35.4-meter diameter central acrylic sphere with 20,000 tons of liquid scintillator, a special material that flashes with light when a neutrino interacts with it, while simultaneously displacing the water. Throughout this entire process, the team achieved and maintained unbelievably stringent requirements for ultra-high purity, perfect optical transparency, and extremely low background radioactivity. All the while, scientists were debugging, commissioning, and fine-tuning the system for its grand debut. At the heart of JUNO is its central detector, an acrylic sphere containing an unprecedented 20,000 tons of liquid scintillator, all suspended at the center of a vast 44-meter deep water pool that helps shield it from stray radiation. A gigantic stainless steel structure, 41.1 meters in diameter, supports this entire assembly, which includes the sphere itself, the scintillator liquid, 20,000 ultra-sensitive 20-inch photomultiplier tubes, PMTs, another 25,600 smaller 3-inch PMTs, along with all the necessary electronics, cabling, and magnetic compensation coils. Every single one of these PMTs works in unison to detect the faintest flashes of scintillation light, produced by a neutrino interaction, and instantly convert that tiny signal into electrical data we can analyze. Professor M.A. Xiaoyan, the chief engineer for JUNO, reflected on the immense challenge. Building JUNO was a journey of extraordinary obstacles. It demanded not just brilliant new ideas and technologies, but also years of careful planning, relentless testing, and sheer perseverance. Meeting the incredibly strict demands for purity, stability, and safety required the dedicated effort of hundreds of brilliant engineers and technicians. It was their incredible teamwork and integrity that transformed a bold and ambitious design on paper into the functioning, reality-based detector we have today. Now ready to open a completely new window into the mysterious world of neutrinos, this was far from a solitary effort. JUNO is hosted by the Institute of High Energy Physics, IHEP, and is a truly global endeavor, uniting more than 700 researchers from 74 institutions across 17 different countries and regions. Professor Gioacchino Ranucci, the deputy spokesperson for JUNO from the University of Milano and INFN Milano, highlighted this crucial international spirit. The landmark achievement we are announcing today is also a direct result of immensely fruitful international cooperation. Many research groups from outside China brought their invaluable expertise to JUNO, knowledge honed from previous liquid scintillator experiments around the world. The global liquid scintillator community has collectively pushed this technology to its absolute ultimate frontier, which is what has paved the way for the ambitious physics goals of this experiment to even be possible. Looking far into the future, JUNO is designed for a long and productive scientific lifetime of up to 30 years. But the vision extends even further. The collaboration has a credible upgrade path planned to transform JUNO into a world-leading facility for searching for an event so rare it has never been seen: neutrinoless double beta decay. Now, this is a point that could spark major debate. If such a decay is ever observed, it would prove that neutrinos are their own antiparticles, so-called Majorana particles. A finding that would fundamentally rewrite textbooks and directly probe the absolute mass scale of neutrinos. This would address fundamental questions that span the entire spectrum of science, from the tiniest particles to the largest scales of astrophysics and cosmology, profoundly and permanently reshaping our understanding of the universe's very origin and ultimate fate. So what do you think? Is determining the mass ordering of a nearly massless particle the key to unlocking a new theory of physics? Do you believe such massive, international scientific collaborations are the best way to tackle these universe-sized questions? Share your thoughts and opinions in the comments below.